Hello everyone to another video. I'm your host today, Daniel Dolz, here to present my most recent work about the reverse water-gas shift reaction over a MXene catalyst, using three different methods: DFT, microkinetics, and Kinetic Monte Carlo.
So my boss told me that I have creative freedom as long as we are not cancelled. So I'm sorry, Francis.
So, first of all, what is the reverse water-gas shift reaction? Well, it's a water-gas shift reaction, but inverted. I don't know, man. The catalyst used is molybdenum. It's a molybdenum-based MXene with carbon, and to understand more about this MXene catalyst, my friend Diego did a magnificent job explaining it in another video in this channel, so I will escape the explanation, and the only needed information is that I used a 3x3 MXene supercell, and this supercell has four different symmetry adsorption sites, which are the ones that will be used in this study, namely the top, the bridge, and two hollows, a hollow with a carbon and a hollow with a metal. As for the reaction, three different pathways will be studied: the redox dissociation and two associative paths, the carboxyl path in green and the acetate path in red. All the molecules involved in the reaction were adsorbed in the four different sites explained before, with the different conformations. The most stable absorbent site for each molecule is shown on the right. All these adsorptions were characterized using DFT, using the VASP code. Also, all the transition states were found using the CINF method. I have the perfect image to illustrate how the process to find these transition states is usually found. This is an example of a diffusion between two or three different sites with the same energy. In the first barrier, you have a possible transition state, then something happens. You don't know what happened, the program doesn't know what happened, but everything explodes, and the only explanation and the only thing you can do is to read the calculation, and finally you obtain a new transition state which is lower than the one before, and it's usually the correct one. You have to check by characterizing Y frequencies, but now, in order to prepare for everything, I will show you how to prepare the perfect VASP calculation. With this explanation, then we have the microkinetic calculations made by used by a program named MXenes. It's a very intuitive program that is very fast, with calculations made in less than a minute, and only information of the energy barriers of the different steps are needed. Another great quality of the program is that the graphics and the analysis is done automatically, so the workload is reduced. It has some cons though. The crucial information of the simulation is not present, for example, collateral interactions, and the graphs created, let's just say, that are passable at best. Finally, we have Thacros. Since I started using this program back 2 years ago, I have always said that Thacros is something like Gordon Ramsay. It's very good at what it does, but it's also very picky. So the video is long enough already, so I won't explain what these inputs and these input files are or why I need it. It's very good. It's perfectly explained in the Thacros manual in their web page. So people, this is me. You have seen me before, and people that know me can tell that something I love is Pokemon. So I'm gonna make an analogy using Pokemon to compare the two programs. MXenes is Rayquaza. It's very good, but has a fatal weakness that prevents it from being amazing. In this case, in the case of the program, it's that lacks the information of several of the reaction steps. Thacros will then be my Rayquaza, which is slightly better, but it takes a lot more time to set up, like Thacros. Both of those programs need the rates of to calculate the rates of each step on the reaction. This is how it's calculated. I won't explain it. So let's start with the results. First of all, we have the DFT analysis, starting with the drift free energy. This was computed for a number of partial pressures and different temperatures, and was shown that for it to be fireable, it needs a high temperature, a high reactant partial pressure. With the DFT calculations, we made a Gibbs free energy profile. For these different pathways, we found that the most favorable would be the redox pathway, followed closely by the acetate pathway, which could mean that they are competitive with each other, but the carboxyl pathway seems unfavorable. In the microkinetic analysis, however, shows a preference for the formate pathway at lower temperatures, which is counterintuitive, shown by the presence of these two species. It has a higher energy barrier, so there should be a reason, but what it could, we can have some hypotheses, but we should first contrast the results with the Kinetic Monte Carlo simulations to see what those simulations tell us. These simulations show a peak performance at 600 Kelvin before the decompensation of the catalyst. Before showing the KMC results, I would like to make a representation of a number of troubles I had related to the KMC simulations. I consider this important to add in the video because normally we only show the final results of our research, and it makes seem that everything has gone smoothly from the beginning, and I think I can speak for everyone, but this is not the case. Data is lost, results are in disagreement with previous works, something happens and everything explodes, and a large number of etc. So the important part of all the studies is to be persistent. So anyway, let's see a compilation of things that happened to me. So now starting the KMC analysis, I have a short video. This is a simulation of different steps of the Kinetic Monte Carlo simulation and 700 Kelvin. Everything is included, from energy barriers to lateral interactions and everything. We can see that at first the lattice is complete. That very quickly a lattice is completely covered, which is a common occurrence, and this is also an explanation of the appearance of the species from the acetate pathway in the microkinetic simulation. The redox pathway cannot occur if there is not at least a free site on the lattice. So the next best option is to react to form these species to free sites. At this temperature, we observe that when the still state is found, the majority of coverage is either oxygen or atomic oxygen or O2. In the simulation, however, instead of obtaining the peak performance at 600, the peak is found at 700 Kelvin, before the catalyst decomposition. If we compare the occurrence frequencies at the different chosen temperatures, 500 Kelvin, 785 and 850, we find a possible explanation. First, we will not overlook the effect of lateral interactions. Secondly, raising the temperature directly affects the occurrence frequency, and the carboxyl pathway becomes open starting at 700 Kelvin. Thirdly, water is dissolved, which completes the reaction. Finally, as oxygen is involved in processes like O2 generation, the backward redox pathway is blocked and serves as a way to free sites by desorbing. At 800 Kelvin, the occurrence of this phenomena is skyrocketed. This is the end of the video. I would like to thank all the sponsors, from FEDER to the Ministerio de Ciencia e Innovación y Universidades and the Agencia Estatal de Investigación with all these projects, to María Maezdu with those projects, the Red Española de Supercomputación, because without it we couldn't do many calculations, the AQTC, which is where I belong, and the Generalitat de Catalunya for the PhD grant I have, and to me think for a predoctoral grant given to one of my colleagues. Thank you all for watching, and see you in the next video.